Thank you everyone for attending our Tech Talk today. We are absolutely delighted to have our friend and colleague from MUSC, Dr. Jihad Obeid, who will discuss machine learning methods to predict the risk of suicide. But before I introduce him, let me mention some housekeeping issues. So we will continue to extend CME credits for our Tech Talks and our ID series presentation. The information will be distributed through email to those that registered for today's event. If you did not register prior to today's talk, you can still obtain CME code information from Lisa Maturo at Christiana Care, and her email address is in the chat. Our September 23rd ID series, we will have Madeline Brooks, who is one of our own from Christiana Care, who will discuss spatial analysis of Newcastle County COVID-19 testing. So you really do not want to miss that presentation. And then on October 7th, we will have another tech talk from Dr. Callie Kneel from University of Delaware, who will talk to us about his research regarding the role of wastewater epidemiology and lessons learned from COVID-19. So that will be already also a very, very interesting presentation. So again, I'm really delighted to introduce Dr. Obeid. Dr. Obeid is Professor of Biomedical Informatics in the Department of Public Health Sciences and the Department of Psychiatry at MUSC. He is also the division head for Biomedical Informatics, Health Systems and Policy at MUSC. MUSC is Medical University of South Carolina, and also the co-director of Biomedical Informatics Center for the MUSC CTSA. He obtained an MD from the American Medical University of Beirut in Lebanon, did a pediatric residency at Duke University, a pediatric endocrinology fellowship at Cornell University, and also a medical informatics fellowship at Harvard Medical School and MIT. Jihad has been co-investigator on and is co-investigator on numerous NIH grants and center grants for which he leads a bioinformatics team, and has been also the PI on several NIH grants. He's a teacher and a mentor, has multiple publications, and leads a large number of CTSA-related informatics projects, such as the Electronic Health Records Research Data Warehouse, I2B2, RedCap, and several others. We know him as an expert in machine learning, deep learning, and other AI techniques, and is also a very active member of our ACCEL CTR BIRD, Biostatistic Epidemiology Research Design Core. So thank you so much, Jihad, for being here, and we really look forward to your presentation.
Thank you, Claudine, for the kind introduction. I'll dive right in because I have a ton of slides, and hopefully we can cover most of them. I'll zoom through some so that we get a chance, hopefully, to do some discussion towards the end. Okay, so thank you for the invitation again. I am delighted to be here and present to the Tech Talk today. I've done a similar presentation on a different project a couple of years back, but I think there's a lot that has been done since then. So this project today is the motivation for it obviously is suicide prediction. And why would we want to do that? As you all know, it's the epidemic that preceded the pandemic. There's a significant number of deaths in the US every year. And it has been exacerbated quite a bit by COVID. There's been there is a need to identify patients at risk and also a need for surveillance. And there's for predicting, it's good to identify patients at risk because there are things that you can do for patients. You can refer them for treatment or other types of either medical management or other type of new cutting edge treatments. And then for surveillance, of course, it's useful for population health studies and estimation of the cost to society. So I'm going to start this presentation by giving you all a little bit of background on AI and the different ways we've used it here at MUSC for a number of projects. And then I'll dive into details of the methods. Um, for AI, as you all know, AI is not new. It's been around for many, many years. And machine learning is a subset of AI that involves data. Uh, and deep learning is the newest iteration of machine learning, and it's become popular more recently because of the advances in computational power. So when we talk about deep learning, basically, I'll explain what deep learning is in a minute. But first, a little bit of background on machine learning. As you all know, there is supervised and unsupervised machine learning, and you'll see why this is relevant. So supervised means you know what the outcome, and you give the data with the outcomes to the algorithm, and the algorithm learns from the outcomes. Whereas unsupervised, you don't know the outcomes. It's algorithms like clustering to identify patterns in the data, or to cluster different buckets of data together and identify patterns. Those are the main two types. Most of the work that I do is under supervised learning, but I do leverage sometimes unsupervised as well. Some examples of supervised learning algorithms that you may be familiar with are logistic regression, which is one of the simplest types of machine learning, naive Bayes, classifiers, decision trees, random forest, and artificial neural networks. And deep learning is really an advanced form of artificial neural networks. So I'll take a little bit more time to explain what that is. Our ANNs are made up of multiple artificial neurons, and each neurons or node is made up of a function that's called an activation function that takes input and an output, and then you put them together in a number of layers, and based on the data that you give to the algorithm, and you can do several iterations, and there's an algorithm called gradient descent, by which you run the algorithm several times, and it starts identifying those weights that are the arrows between the nodes. And basically what happens is that a trained model is a model that has refined weights that can provide an approximation of the output based on the data that you give it. And there are many different types of activation functions, and it depends on what part of the part of the ANN you are. You can use different types of activation functions. For example, typically in the hidden layers, you use something called a ReLU, which is almost a linear linear function. And then for the output, if you're predicting a binary output, you use something called the sigmoid or logit function, which basically predicts a 0 or a 1 or a probability in between. Whereas if you have multiple outputs, you could use an activation function called softmax, which can give you one of several outputs, not just a binary output. So in text classification, my research is basically focused on text classification using electronic health record. But text classification is not a new concept. It's been used in other industries many times. And you're probably familiar with sentiment analysis like book reviews, where you provide a lot of data to the algorithms and then they learn whether it's a positive book review or a negative book review, like Amazon reviews, also movie reviews and things like that. And there are many ways to do that. You could do that just by looking at word frequencies in those text corpora, or you could look at, or you could use more modern, like deep learning classifiers, which is what we're using in some of the algorithms here. So what is deep learning? I mentioned that several times, but basically it's artificial neural networks that are made up of many layers. And as you can see in this schematic here, this is a deep convolutional neural network. that is learning basically face recognition, and so it's a multiple. It's not a binary output. And you could see that across the different layers, a deep neural network can learn patterns across the different layers. So, for example, it starts learning the edges, different angles of the edges and where to identify edges. Then on the secondary layers, it can start to learn different parts of the face. Then it can start identifying face in a picture. And then finally, it can start identifying a person. And so it turns out this type of model also works well, slightly modified, of course. It works well with pattern recognition in text. So, another thing that I wanted to point out for those of you who come from a statistical background, you'll hear us in machine learning talk about features instead of predictors, and labels instead of outcome or response. So, and another thing we talk about, if you want to give a supervised learning algorithm, you give it labeled data, meaning data that you know the outcome for, and then you can predict labels on the test data. So a typical way you would do that is you get your full data set and you divide it into training and testing data. And then within the training data, you can, if you want to do a true test of your algorithm, you take aside a data set that's called the test data. And then you play around with the algorithms and fine tune them using your training data. And you could divide it into training and cross-validation. And often you see challenges that are announced on things like Kaggle or other like I2B2 challenges, where they give you the training data and they hold out the test data for a true test at the end by which they measure your algorithm. And there are many ways where you could do the training. You could do k-fold cross-validation and do several iterations to identify and fine-tune your models before you test on your test data set. All right, so this is some examples of projects that we did here at MUSC. The first one was altered mental status, which I presented on several years ago. And the motivation for that was that we wanted to try to identify altered mental status in clinical text because it's useful for pulmonary embolism. So we ended up actually comparing deep learning models with the traditional bag of words or word frequency models, and we showed that deep learning works a lot better. And we ended up publishing this a couple of years ago. In BMC Biomedical Informatics. If you're interested in the details, this is the link to that. And the other good news is that we got, a couple of years ago, we applied for a Delaware ACCEL, Delaware CTR pilot project. And the nice thing about this one is that we wanted to prove that the models work well across institutions. So our aims was to test and validate our models at Christiana Care and see if we can improve the training, cross-training across institutions, something called when you transfer the models from one institution to the other, it's called transfer learning. We also played around with de-identification. You can imagine that de-identification is useful for privacy preserving methods when working with clinical data. So we wanted to see if you de-identify clinical text, and there are many algorithms to do that, does that ruin the data that you're working with? So we wanted to test if the fidelity stays there and the utility of the data for machine learning. And we did this experiment where we identified several tokens that were considered PHI. We removed those, or technically they're really PII, and we removed those, about 2,000 of them. out of several thousand. And and the bottom line is that we found out that there's not a big difference. So it doesn't matter if you de-identify the data. We tried several different models. In fact, if you look carefully at this graph, the de-identified is in red. You'll see that the de-identified data actually removes some of the noise in the data set, and it tends to be a little better, especially in the deep learning models. And we also published that at MedInfo. So the second use case I wanted to describe really quickly is we have another pilot-funded project to look at cirrhosis patients and see if we can phenotype cirrhosis, and that's important for recruiting patients for clinical trials or retrospective studies or early identification of patients at risk. So we ended up also doing some manual labeling of a test data set. We were able to leverage a registry that of cirrhosis patients that we had here at MUSC, use that for training. And again, here we showed that deep learning models are far superior to word frequencies, and it was and we again published this in Journal of Clinical Gastroenterology. And I'll show you why I'm talking about cirrhosis, because we used that to do some more experiments on that pilot grant. A third use case is more related to prediction rather than phenotyping. The first two examples I gave you are phenotyping, meaning identifying patients with certain characteristics. This one was motivated by the COVID pandemic early on. We did a study back in April of 2020, where we wanted to try to identify patients that come through our virtual care clinics, because the data collected in virtual care was only in text format. So we wanted to be able to prioritize patients for testing. As you remember, back then there was limited resources for testing. So we wanted to basically predict which of these patients, based on their symptoms, were COVID positive by PCR. And the short story is that we used a similar algorithm using word embeddings and a convolutional neural network, and we were able to test train the data on a few hundred patients. We didn't have a lot of patients back then in April of last year. And we were able to get a decent AUC. This is on the test data set, but this is the real test was on the test data set. Training versus test data set. We reached an AUC of around 0.73. And we were able to publish this at AMIA. I'll show you that link. But the interesting thing about this study is that simply looking at the COVID positive notes in virtual care versus the COVID negative notes, we were able to identify smell and taste very early on, even before the CDC announced their addition of these symptoms to their guidelines. So we just beat the CDC by a couple of weeks. And we published that at AMIA, as I said, back in April of last year. It was finally published in July, though. All right, now moving on to the suicide project. So we started this work early on in 2019 when I had a colleague of mine here at MUSC who's a psychologist who was interested in trying to see if we could use that methodology, the deep learning methodology, to identify patients with suicide. And more importantly, if we can predict patients that would come in with suicidal behavior. Now, since we don't have very good death data here yet, we don't have that yet, we ended up using a proxy for suicide death. and that is intentional self-harm. And the other thing, so we had two aims in this IRB protocol in this study. One is to see if we can do phenotyping of intentional self-harm, meaning identify if the question was, can we identify patients that have suicidal behavior just based on their clinical notes, so automatically read the notes, in other words. And the second aim was to see if we can predict future intentional self-harm behavior based on historical data. So what we did is, we have this infrastructure here at MUSC where we have a research data warehouse, and we also pre-process the clinical notes from EPIC so that they're more amenable for extraction and use for research. And then we have a process by which we request data from the RDW using our data analysts, and we can create a research data mart that are project specific if you have IRB approval. So we did that for this suicide prediction project. And so we had this IRB approval, and the clinical notes span 2012 to 2019. Remember, this was done back then in 2019, preceding the pandemic. And we ended up restricting our records to patients over 20 because we wanted to look at historical data by 2 years, so we wanted to look at only adult clinical notes. And we identified, patients based on ICD codes for intentional self-harm, and there are very well-defined codes by the CDC. So we didn't invent this on our own. Luckily, the CDC have published a report identifying clearly what intentional self-harm codes look like, and there are hundreds of them. Whereas for suicidal ideation, there's only a couple of codes. So we did that. We identified a bunch of patients that had either intentional self-harm or suicidal ideation, and we looked at records of controls which had neither. So the model that we trained were only for intentional self-harm. And we used for the features, if you remember, the predictors are basically the words in the clinical notes, and the outputs or the labels are the whether they had an intentional self-harm code by ICD. And we also did, the true test, the gold standard. We did a couple of hundred charts were manually reviewed to confirm the accuracy of the ICD codes. This is just a quick overview of the software stack. So we use a combination of R and Python and an open source library from Google for most of our deep learning models. And we leverage GPU hardware, using the NVIDIA CUDA libraries. The note types that we looked at were primarily from progress notes, plan of care, and ED provider notes. So not just ED notes, but across the board. So because there were a lot of notes for each patient, even when you're looking at concurrent notes that coincide with the ICD codes, there's a ton of notes in there for each patient. So we had to come up with a way to put the notes together, and because we didn't know which are the important notes. So we put the notes all together. We stitched them together using a concatenation, and we created basically these long text documents, and we ended up classifying on these long text documents. So you could imagine some of the text documents had relevant information, others did not, and for the intentional self-harm, some document types may have relevant information, but like if it's a trauma note, it may not. But if you stitch them together, you can ensure that the signal has to be in there somewhere. Whereas for the control, the hypothesis is that they have no signal whatsoever in the whole clinical note, set of clinical notes. So, and we had to cut it off just for computational efficiency. And it turns out that we capture the majority of the records by cutting off at a certain level. So for the phenotyping task, which is looking at labels or ICDs that are concurrent with the clinical notes, we had several hundred patients that had intentional self-harm, and we about twice as many controls that did not. And we tried to, and we did, we estimated a number of patients that had intentional self-harm by ICD, and we manually reviewed 200 records that are balanced between positive cases and negative cases. So this was really our gold standard set that we used for testing. Okay, so I mentioned the ICD codes, and they are fairly large number of ICD codes that are used for intentional self-harm. So it turns out that the ICD codes are pretty good in our records at MUSC. In fact, we only had a handful of cases among the 200 that were false positive and no false negative. And among the false positive, I mean, they were suspicious. They had past history of intentional self-harm. Remember that we were looking at concurrent self-harm. And two that were suspected, someone in the record mentioned, suspicious behavior. So basically the ICDs are fairly accurate in our hands here at MUSC, specifically for intentional self-harm and specifically for the ones defined by the CDC. For the prediction, so for the phenotyping task, we look at concurrent nodes. So if you look at if you think of the visit where we had intentional self-harm recorded by ICD as the index visit, or t equals 0, so that's the phenotyping. You look at those nodes. Whereas for the prediction, you want to take t equals 0, but you don't look at nodes. You look at nodes only before that. So we chose a time window about 180 days prior up to 130 days prior. I'm sorry, up to 30 days prior. And we concatenated nodes up to a certain amount. We didn't concatenate the whole 6 months window, again, just for computational efficiency. And so for the prediction, we used only ICD codes, since we showed that the ICD codes are pretty good. Also, I forgot to mention that in both cases, to test real-world data sets, we divided the data across time. So we used the data for training from 2012 to 2017, and we used the data for testing from 2018 to 2019. So this is sort of like a real-world hold-up test set. We did that as a challenge to ourselves. This is just to show the type of pre-processing. We again here compared for the phenotyping task, we compared bag of word models or word frequency based models, and there's some text pre-processing that you have to do for those who are interested. And the deep learning models that we used in this particular use case was convolutional neural networks and long short-term models. I'll explain those a little more in a minute. The other thing that you have to, for the word frequency models, you just look at algorithms that are called bag of word that look at, and there are ways to harmonize using something called term. I showed you here TF-IDF, term frequency inverse document frequency for word frequency models. But for the deep learning models, you have to use something called word embeddings, which is basically conversion of the word sequences into word vectors. So the nice thing about that is that you preserve the sequence of words, and you can imagine how that would give you more information. So how do you do word embeddings? There are multiple ways to do that. And you basically you convert words to tokens, and the tokens then you give them to the algorithm, and the algorithm can learn the n-dimensional vectors for each word. And there are many different algorithms to do that. The one we tested here at MUSC is actually an unsupervised method called word2vec. And today there are many other methods, but back in 2019, this is all we had available to us. And it's also computationally relatively easy to implement. So with word2vec, you can give it a whole bunch of data. You don't just have to give it labeled data. You could give it all the clinical notes, and it learns a little bit about the context of the different words based on the clinical notes that you have. You could train them also you could pre-train them also on PubMed data. So many people have published word2vec models based on PubMed case reports or just, all of PubMed. But we didn't do that because we did a little bit of, slightly different pre-processing of text, and we wanted to have a fair advantage for pre-training using our own text pre-processing. So we ended up training a word2vec model on our clinical notes from all the clinical notes that we had, not just the labeled notes. So for the phenotyping task, we just did, remember I told you we divided data into training and testing. We fine-tuned the models using the training data only, the 2012 to 2017. And we looked at all of these different models, including those two deep learning models. And the deep learning models look something like this. The CNN, the convolutional models, which are typically used for image recognition, and I said earlier that they worked well in our hands for text classification. There's also something called the LSTM model, which starts with the same type of word embeddings. But instead of using convolutions, you use LSTM layers. And then from there, similarly, you have a hidden layer here and a sigmoid output layer that predicts yes, no for intentional self-harm. Now, before moving on to the results of this preliminary work, before we did any of the machine learning experiments, we looked to see if there's any characteristics in those clinical notes between the negative and the positive notes, and it turns out, yes, there are differences between the positive notes and based on word frequency. So you have things like SI trying to show, we didn't know before we started. So it turns out words like SI and suicidal are important in adding to the predictive model, just based on chi-square frequency analysis. And there are slight differences between predictive nodes, prior to the intentional self-harm and the concurrent nodes, but not huge differences. Also, with easily interpretable models like random forest, you can see similar results where the word suicide. Remember, I forgot to mention, but it was hidden in that pre-processing slide, that one of the things you do is you stem the words to reduce the amount of data you're dealing with a bag of word models. So you could see here some of the 10 important words are suicide, overdose, SI did not stem, and attempt. All of these are important words that have more important weights for the random forest. So the random forest, although it wasn't as good as the deep learning model, and I'll show you those results, it's really nice to use because it's easier to interpret. Okay, so I mentioned the word2vec that we used all our clinical notes for and we in this IRB approved protocol, we had over 800K clinical notes. We used all of these notes. We submitted all of these sentences. We chopped them up into sentences and gave the whole, thousands of sentences, hundreds of thousands of sentences to Word2Vec to see if it can start learning the context of words from these sentences. And you could see that the algorithm worked because basically what you're doing here is you're clustering similar words together. And remember, I said we did that for 200 dimensions, but we did a t-SNE plot by reducing the number of vectors from 200 to two-dimensional. And you could see like similar words start clustering together. So things like attempt and suicide and gesture and even misspelling of gestures are starting to clump together, meaning that the algorithm is learning contextual importance of words, even before you give it labeled data. Okay, so I mentioned the training for the fine-tuning of the models. So we were able to identify, just using the training data, training cross-validation, that the deep learning models are superior. So we decided to focus only on the deep learning models for the test data set. So how did we do? With the phenotyping task, we did great. It was surprising, but actually the other thing that's important about this is that it shows us, even before we did the ICD code accuracy manually, you could see that the models are learning very well, and you could see that from the learning curve, which I'll show you later. But bottom line, what we were able to show is that that convolutional neural network and LSTM are able to learn how to read the clinical notes even without ICD codes, and tell you which patient had intentional self-harm and which patient did not. And we confirmed that, like I said, with the gold standard manual review. And what this reflects here is the false positives. So the accuracy went down a little bit because we had some false positives in our data set. But you could see, we had near ceiling results. The CNN without the Word2Vec was the top performer, although there's hardly any difference between Word2Vec and non-Word2Vec performance, at least for the phenotyping. So let's see how we did for the predictive task. So again here, the true test was using the same 4 best performing deep learning models. We used test data sets from 2018 to 2019, and we were able to show that the CNN were slightly better than the LSTM. This is compressed here. We're looking only at 0.75, but they're all, pretty good, all with an AUC above 0.8. Best performer here again was the CNN with random initialization, i.e. no Word2Vec. But again here, if you look carefully, the Word2Vec did not harm the model. And the other thing that's interesting is that if you look at the number of epochs or number of cycles you use to train the models, the Word2Vec one, it has some advantage because it's reducing the amount of cycles that you need. So there's some pre-training that's helping here with the models, and that some transfer learning going on, meaning that some pre-training helping ahead of time. And this is, you could see the pre-training, and we've shown that before when we're working with the AMS data, that Word2Vec, although it does not improve the final accuracy and AUC of the models, it does shorten the number of cycles that you need to converge on a good model. Same thing for the intentional self-harm. Okay, so if I'll stop here for the preliminary work, and I'll start talking more about future work. But if you're interested in looking at the details, again, this one was published mid last year, and here's the link to that. That was published in J. Meir Medical Informatics. So so we were able to secure funding for 1 year from the NIH, from the NIMH, mental health, for looking to see if we can compare traditional models to our deep learning models. And the other thing we wanted to do is to see if our models work just as well at other institutions. So I used my collaboration with the colleague that I mentioned earlier, who moved on to University of South Florida. And so we decided to use our data sets from both institutions to see if we can reproduce or validate the models over there. And the other thing we said we would do is see if we can. So the two aims are to create the infrastructure. And the nice thing now is that if we have NIH funding, we can start getting death data. And that was an important reason for getting this funding. And so the aims are to create the infrastructure and then to actually implement some of the models. And the model that we're going to use for structured data has been published by Simon et al. They used a model using data from multiple institutions. And so we're going to try to replicate that. We've already started collecting some of this data, but we haven't started testing. So it'll be very interesting to test this model head-to-head, same time frames with the performance of our models. Now, what they published is very similar to the AUCs that we published using our models, but it's hard to compare because we really need to compare apples to apples. So that's why we got this funding. Okay, so for future directions, we want to look at explainability. I think Dr. Wolf, a couple of last month, I think, talked about the importance of explainable models, and she mentioned the importance of using explainability in random forest. But what if you're using deep learning models? They're traditionally, thought of as black box models. But there are ways now to look at black box models and see what is the deep learning model picking up. And that's also an active area of research. For our experiments here at MUSC, we started looking at explainability in the cirrhosis project. This is, just for comparison, the random forest, picking up the important words for the phenotyping experiment. And what is it learning, the deep learning model, what is it learning, and how can you identify the important words? So an easy way to do that is you could chop up your documents into sentences and just look at the important sentences and then highlight the important sentences. So you could see things like lactulose dose recently decreased is important because typically patients with cirrhosis are being treated with lactulose. And this is another important sentence. So you can start getting some information even without from the deep learning models using this very simple algorithm, which is just chopping up and exposing that to the trained model. There are some more advanced ways of doing that and looking at the trained weights. Remember, I mentioned the trained weights in deep learning models. So there are ways, people that have done that for images where they can highlight the important parts of the image. For example, this one, they're looking at classifying models for dogs and cats and highlighting the cat, and highlighting the dog using an algorithm called GradCam. So you can adapt GradCam algorithm. It's not easy, but you can adapt it and start highlighting important sentences and important words. We're just starting to play with that. Another important things that we have to look at is the different, you remember I mentioned LSTMs and CNNs, but also there are some more advanced models. And you remember that we weren't getting very good results with LSTMs. So we ended up using, we wanted to test, why is this happening? And one of the hypotheses is that, those advanced models don't do as well as convolutional models with lower amounts of data, which is important when you're dealing with EHR data. Your N is often, especially when you're dealing with private data at one institution, your N is important. So you often don't have the luxury of dealing with thousands of records. So we did this experiment with PubMed case reports, which are a good simulation for clinical notes. And we used mesh terms as labels. And you could see that, I mentioned that we were using Keras and TensorFlow pipelines. Um, uh, so it turns out with Keras, the CNN is the best performer at those. And we don't get very good consistent performances from those other deep learning models. Whereas you could also use, instead of Keras, something called PyTorch, which is another Python-based deep learning library. And we're starting to get a little more consistency between the different models using PyTorch. So there's something weird happening with Keras, but the CNN perform really well with Keras anyway. And it's easier to use and less computationally intensive. So we may end up sticking with Keras for some of the experiments. The other thing we want to look at in the future is look at federated learning. I mentioned the project with Christiana Care, and we published some results with Wake Forest, a colleague of mine. We were looking at a different type of model for a very simple model looking at risk factors for cancer, lung cancer, in fact. And the idea here is that you take data from both institutions and you take an algorithm and bounce it around, and it learns a little bit from data here and a little bit from data there. And you get basically a model trained on data from both institutions. And the hypothesis is that you have a best of breed model that is trained on very diverse data sets. And we showed that such a model can perform better than data trained at one institution. So that's called federated learning. And there are many different ways to do that. And so we want to try to play around with that and see if that improves our AMS model with Christiana Care data. Okay, so the summary of all of this is that I think a good take-home message is that with phenotyping, you can do a lot better than you can do with predictive tasks, and that's expected because often when you're using old clinical notes, some of the notes may be relevant, some may not. If you're using and also prediction by nature is more difficult than phenotyping. But we did show in all of the different use cases, the phenotyping use cases, that you are able to achieve near ceiling performance. So if you're looking for certain characteristics for patients, you can automate that very well, whether it's for surveillance or recruitment for clinical trials, you can do very well with deep learning models. Also, the other thing that we learned is that that's much better than just based on bag of words or word frequency models. So the preservation of word sequences is important. Word effect does not add much value beyond the value of reducing the number of cycles that you need for training your models. And then the future directions that we're going for is to try other transformer-based models. These are the much newer. I mentioned word effect, but now there are more advanced word classification and NLP models that we haven't tried yet. And then possible use in combination with structured data using something like ensemble models, and then we need more labeled data, and hopefully the National Death Index data will help us with this project, and we plan to validate at other institutions. Eventually, although it's out scope for the current funding, we're going to try to get some more funding to look at explainability and perhaps in the future for clinical decision support implementation. Conclusion, it's a little repetitive here, but state of the art AI not used yet in this field. Deep learning works really well because we think it's important because it preserves the contextual context and content and clinical notes, and has not been used a lot for phenotyping, although now it's becoming more popular. And we plan to get future R01 funding to look at those interesting problems that I mentioned before. And this it takes large amounts of teams to accomplish this. So I want to acknowledge my collaborators on the different projects. We have a fantastic team between MUSC and Christiana Care that are working with us, between clinicians and technical teams. My collaborators at Christiana Care are Dr. Nomura, who's an ED doc, and Claudine, who's on this call, who's helping us review some records. And of course, we have a clinical team for the intentional self-harm project and one for the cirrhosis project, and different teams for other projects that we're working on today. So I'll stop here and we'll take some questions and then a break, hopefully. Claudine, you're on mute. Famous last words. I can't hear you. Okay, try now. Is it just me?
No, I think it's me. Can you hear me now?
Okay.
Yeah,
Yes.
I had forgotten my microphone on my headset. Thank you very much for this really very comprehensive presentation. Any question? The audience?
Claudine, I did. This is Scott.
Go ahead.
Okay. It's very interesting. I'm pretty naive about artificial intelligence methods, so I was trying my best to follow along. But thinking more from like a translational or clinical implication perspective, it seemed that you were able to predict the likelihood of an intentional harm event based off of clinician notes who were documenting things that I think on a face valid way would, make sense. People are talking about suicidal ideation or whatever gestures. So I guess my question is, does your model, is the utility of the model to improve upon a clinician's judgment, or instead is it to try to, in aggregate, be able to look at many patients at the same time and identify them for some other type of intervention? Because it sounded to me like, based off of the notes, many of the clinicians were already onto the fact that this patient was at risk.
Yes, that's a good question, and it's often one that you have to address in critiques, both in papers and in grant applications. It's not just me who is looking for, or not just our team who are looking for better ways to be able to identify patients at risk. There are yes, it is important to identify patients at risk for referral to management. And sometimes, and that's particularly important in primary care settings where patients, clinicians are very busy and often do not pay attention to those signals that the patients are referring to. They may be documenting some of them, but may not have, the resources to refer enough patients. So it is important to continue to look for improved ways to identify patients at risk. And all we're doing here is adding a new method to do that using clinical notes. And yeah, we're showing that people are missing signals from EHR documentation. And there may be some other symptoms. We may be able to be picking up at some other risk factors. When you use traditional models, even without clinical notes, you're looking at things like depression and other like different types of treatments that may be documented in a clinical note, but are not seen or not enough hints for people to refer patients.
Okay, thank you.
So we have Ode Dwikat. You have
Yeah,
your hands,
yeah, thank you.
and
Thank
then
you.
Dr.
Mhm.
Pachter. Go ahead.
Thank you, Dr. Jihad, for this impressive presentation. I just have a technical question on the balancing data. When you build all of these models, you said you oversample the data. However, excuse me, when you're testing your data, you also oversample. So because I noticed it was 100 and 100 and 106 and 106.
Yes.
So in the real world, because I'm working now on such model but on different area, when we test the model and needs to generalize any model, we pick a random, not a random sample. We took the sample, but the tested data is not general. It's not balanced. So do you have you tested your models on unbalanced data?
Yes. Let me see if I can bring that slide up.
Yes, please.
Uh, Yeah, this one. That's a
This
very
one, yes.
astute
Yeah, yeah.
point. Yeah. So you are correct. We did end up choosing a balanced data set. And the reason, and this is not by oversampling, it's actually by undersampling. So we just removed the controls. We took a lot of the positive cases randomly, and we selected an equal number of controls. And the reason we wanted to do that is just to get a good estimate of the accuracy. As you know, the accuracy and the sensitivity specificity don't make a lot of sense when you're looking at an unbalanced data set. And for this particular project, we didn't look at the unbalanced data set, but for the COVID one, we did. And then over there, it's important to select your threshold, where you want to
Sure. Yeah.
take, depending on what kind of risk level you want to cut the threshold on the AUC to pick the adequate sensitivity and specificity. And, you start talking about, instead of, because the data is unbalanced, you start talking about sensitivity or specificity in the 0.2 range instead of over 0.5. But, we intentionally balanced the data here just to get for practical purposes and to get a good estimate of the sensitivity and specificity, in addition to the AUC.
Yeah. Thank you so much. Because when I'm doing that without unbalance, sometimes when I train the model, I get, let's say, 90% AUC. But when testing the real data, I get 60% or sometimes 55. I will not say it is tossing a coin, but this is the reality between what we developed on the theory and what's actually
Yeah, that's
yeah.
yeah, that's interesting. Theoretically the AUC should not go down, although the F maybe it will. That's a good point. I have to take a look at that. But definitely the sensitivity, specificity, and F1 score would go down for sure when you have imbalanced data sets. The accuracy obviously would also shift.
Thank you, Dr. Jihad. Thank you.
Lee?
Yeah, hi, thank you. Actually, I have two questions, and they relate to both of the previous questions. One's methods and one's more clinical. So methodologically, you divide your sample into training and testing. Is there a rule of thumb for like a ratio of how many you have to train versus testing, or is there some sort of way that you figure out how many you put into each of those categories? And then the second question is more clinical. Your new NIH study is using, I guess, as the outcome or the label deaths, and I assume that that's deaths by suicide. And are you doing that because obviously clinically, this idea of intentional self-harm, there's a whole category of intentional self-harm, which is called non-suicidal self-injury.
Yes.
And therefore, like your first study was great, but I think it predicts intentional self-harm, not actually suicidality. And is this the reason why you're looking at deaths for the next study?
Mm-hmm. Yeah, so the first problem then is about dividing the data sets. So I think, if you have the luxury of labeled data, you could divide your data, typically people use 70-30%. When you're dealing with a smaller amount of data, sometimes you're a bit more stingy and leaving out test data set because you want to try to, get a decent training. So sometimes we end up like using only 10% for testing. But here, I think, even though we only have hundreds of records instead of thousands, we were able to, divide our data sets across time and use the temporal cutoff and getting, a handful of patients that we can use for testing. Handful meaning hundreds. And it varies across our different use cases. And that's the nice thing about using ICD as labels, because you can, those are automatically labeled using the EHR data. And we hope also using the death index data, we can identify the patients who died by suicide, unfortunately, and use that as a label without manual labeling. You have the outcome there. So going back to the clinical question, so the intentional self-harm, that's an important question. And it turns out, you could look at that link that I put up there for the CDC, but I'm pretty sure, and we had one of our collaborating psychiatry people look at that we did not include in those ICD codes the non-intentional self-harm. The CDC luckily defines those codes very carefully, and we were able to use them.
I'm sorry, I didn't mean non-intentional self-harm, but non-suicidal self-injury. There is a whole diagnostic category called non-suicidal self-injury.
But it is self-harm?
Yes. Yeah. It's cutting, for example, adolescents who cut. They may not have a higher risk of suicide, but it's a separate category. I apologize. I might have said non-intentional when I meant non-suicidal.
Yeah, I remember we did look at that, but I can't remember, sorry, the details, whether these codes were included in our codes or not. But that's a good question. We definitely ended up writing it in the grant. I just can't remember the details because I'm not a psychiatrist. But yeah, I'm hoping, that, like I said before, to get around that, we are just going to use the actual outcome for instead of manual label.
Any other question?
Just quickly on that, a great presentation, Jihad. I really enjoyed it. So I was wondering when your study period was from 2012 to 2019. So when the ICD codes changed from 9 to 10, like, how did it impact your study? And did you were you consistent and just follow specific codes?
Yeah, that's a good question too. But we picked 2012 because and we have Epic notes, Epic implementation in 2012. So we are confident that if there is any variation, it's not a lot of variation across time. But that's something we haven't really tested. But the proof is sort of in the pudding that if you train clinical notes with 2012 to 2017. You are still being able to get good results by testing on the 2018-2019. Now, that may not apply with our current experiment, because now we're looking at notes going into 2020, 2021, and obviously the pandemic is going to have significant impact on the clinical notes. And we already started to think about that with the Florida data, who are collecting data from 2020 to 2021. And our thought is that we are just going to have to divide our patients and pick a balanced enough set across the board, an even number across all years. So that's a very good question.
I have a last question, unless anyone else has a question. Don't see any. Just a quick question about the study population in your first study on phenotyping suicide, risk of suicide.
Oh, suicide. Okay.
Yeah. Did you take only patients who were hospitalized, or it was ambulatory and hospitalization?
Yeah, everything.
Okay. And outcome, same thing. The intent self-harm could have been also ambulatory.
Yeah, let me bring up So if you look at the note types, they're across the board. There's ED, there's H&P from outpatient, there's
I see. Telephone
consults,
encounter.
but the
All right.
majority are progress notes. And I don't know whether I can't remember whether these are primarily inpatient or outpatient. I think they're a combination.
Okay.
Plan of
Right.
care tend to be like after a visit, I would imagine.
Okay. And I have a very last question. The word to vac, I'm a little confused about this because you said that it provides context, around the words, but I mean, intuitively, it should work better than only the simple word classification. So I'm not sure I understand why it doesn't work better.
Yeah. So let me see. So yeah, like you said, we showed that it is learning some context. Um, Now, I don't know the answer to that. We believe, I discussed this a lot with my colleagues, in NLP and computer science here at MUSC. And so you may be learning something from them, but you're not learning something towards the outcome. So it may be somewhat, taking you in a different direction. And so, I mean, as you saw, it's not terrible,
Right.
and it is learning something out of it, but it's not taking us towards our outcome because it's unlabeled data. So that's like, a theory.
See.
And it'll be interesting to test those more advanced models like BERT, the transformer models, the more advanced embedding and pre-training techniques. I'll let you know. That's in a couple of years.
Okay, great. Any other question? All right. Well, thank you so much, Jihad. This was great. Very
You're
informative.
welcome. It's a pleasure.
Talk to you soon. Have a great
Bye.
holiday weekend.
Thank
Thanks.
you. Bye.
Bye.